Ladies and gentlemen, welcome back to Mr. Lee's physics class. So today we will go through the lesson, still in the lesson of chapter 3, electricity. And we'll go through the conductivity and resistivity of a conductor. Ladies and gentlemen, let's observe the diagram. The diagram shows a speed train that or a maglev that travel through the runway. Ladies and gentlemen, objective for today's lesson are, let's go to the next slide first. The objective of today's lesson. In this lesson, you were able to define the resistivity and derive the equation. Explain qualitatively the mechanism of conduction of electricity and semiconductor. Understand the dependence of the resistivity on temperature for metal and the semiconductor using the equation. And final objective, know the phenomenon of superconductivity. Now, let's observe the diagram. This slide shows the variation of resistance with the length. Let's connect, switch on the switch or close the circuit. The battery of 2 volts provide the power supply, provide the electric current through the circuit. When the current flow through single resistor, the current show that is 2 ampere. What will happen if I increase the resistor and arrange it in series? Then we observe that the current from 2 ampere reduced to 1 ampere. And we keep on increase the resistor and the the conductor with resistance. If the conductor, one single conductor with L, so we notice that the resistance is 1 ampere from the calculation, where we use R equal to V over I. When the conductor is double, that means that the length double. When they put side by side or they arrange in series, consider the length increase. Once the length increase, we notice that when the length of the conductor increase, the current reduce. Why the current reduce? Because the resistance increase. The resistance in the circuit increase. We said that the effective resistance in the circuit increase. As a conclusion, we can say that resistance is directly proportional to the length. Now, we observe the resistance against the length graph. Resistance against the length graph, when the length increase, we notice that the resistance is directly proportional to the length. When the length of the conductor increase, the effective resistance in the circuit also increase as well. This slide shows the variation of resistance with the cross-sectional area. Cross-sectional area, that means one let's say the area, cross-sectional area of the resistance, the first conductor is 1 mm square. What will happen? Okay, the current, okay, we switch on first and we notice that the current increase. Once I replace it, the cross-sectional area of the conductor increase and the effective resistance calculate will reduce because and the current cause the current in the circuit increase. What will happen if I change the cross-sectional area, bigger cross-sectional area of the conductor? The current keep on increase and the effective resistance keep on reduce. So from here, we can set that from the graph resistance against the 1 over cross-sectional area. We notice that R is directly proportional to 1 over A. Means while R is resistance is inversely proportional to the cross-sectional area of a conductor. Now, from the combination of the R resistance is directly proportional to the length and resistance is inversely proportional to the cross-sectional area, we get that the resistance is directly proportional to L and is equal to L over A times with the constant. This constant we known as the resistivity, which we learned yesterday. Resistivity means that the ability of the material to limit the current. Okay, it is the ability of a conductor to limit the current in the circuit or resist the current. Now, different material with different resistivity. A good conductor, okay, metal with good conductor, right? So a good conductor, for example, silver has 1.59 times 10 the power negative 8 ohm meter. Copper 1.68, iron 9.71 times 10 the power negative 8, platinum 10.6 times 10 the power negative 8. Okay, and there is another material, one metal that's better than platinum. What is that? That is aurum. Aurum is gold, G-O-L-D. So gold is the best conductor. Second will be the platinum. If you use platinum is very expensive. Okay, so how about silicon? Silicon is germanium 0.6, silicon is 2300. So notice or not, the resistivity of a silicon is very high. How about insulator? Glass and rubber. Glass and rubber is around 10 to the power 9 to giga and tera. Okay, giga ohm meter or to tera ohm meter. How about rubber? Rubber is more than that. Okay, more than the tera. So this means 10 to the power 13 to 10 to the power 15. Next slide. A platinum wire has a length of 1 meter and a diameter of 2 mm. If the resistivity of platinum is 10.6 times 10 the power negative 8 ohm meter, calculate the resistance of the wire. This means that resistance is equal to resistivity times with L over A. So that means use the formula R is equal to resistivity times L over A, and the cross-sectional area is A equal to pi d over 2 square. Okay, pi r square actually. So we substitute in the area into the formula, and we get that R equal to 4 times of the times with the resistivity times with L over pi d square. And substitute all the value into the formula. Finally, we get that the resistance is 0.034 ohm. That means that before that, in Form 5 syllabus, we learned that resistance of a material is directly proportional to the length of the conductor. Resistance of a material is inversely proportional to the cross-sectional area. Okay, this one resistivity we never learned, right? Actually, we learned before in Form 5 syllabus. One of the factor is type of conductor. Resistance effect by type of conductor. That means that different material, different conductor have different resistance. Why? Because different conductor with different resistivity and conductivity, but resistivity as well. As a conclusion, we can say that the resistance of a conductor is directly proportional to the length of the conductor, but inversely proportional to its cross-sectional area of A. Resistance R is given by R is directly proportional to the length of conductor and inversely proportional to the cross-sectional area. And finally, we get R equal to resistivity times with the L over A. Let's look at the slide. The slide shows that the free electrons is moving in the electric field, in the influence of electric field, or in the presence of the electric field. So the negative charge electron with negative charge is moved in the opposite direction to the electric field. That means that what is meant by electric field we learned before. Electric field is a region where a charge experience an electric force. A charge, okay, in the region which experience an electric force is electric field. This means that any charge in the electric field will experience an electric force. So that means that when it moves, we notice that there will be two forces for each of the negative charge, each of the electrons experience. First is the force due to the electric field. Okay, so that means the force is opposite, the direction of the electric force is opposite direction to the electric field for the negative charge. Okay, because negative charge and positive charge, the direction are opposite, the force experience are opposite. So for negative charge now move opposite direction to the electric field is because the electric force produced is in opposite direction with the electric field. There is a force we call drag force due to the collision with iron. This drag force will produce the friction. So this drag force always opposite to the electric force. That's all. Next slide. We notice that the electric force F is equal to E times with E, which equal to MA. Electric force equal to MA. So what we can do, we notice that we want to derive the resistivity. Acceleration A is equal to E over M, where there is a charge times with the charge for one single electron, charge for single electron times with the electric field over the mass of the electron. And A equal to V over T. So from here, E over M is equal to V over T. That means that V will be the drift velocity. Drift velocity also equal to T times with the mean times between the collision times taken, okay, between the collision over the mass. And the current density J is equal to NEV, where is equal to conductivity times with the electric field. Once we substitute everything into the formula, substitute the current density into the formula, we get that T over M is equal to conductivity times with E, where the conductivity will be equal to NE square T over M. So as we know that resistivity is 1 over conductivity. So this means reverse the formula. This means that M equal to NE square T. So this means that here is the derivation between the electric force. We use electric force equal to the drag force. Electric force EE over, what's that? EE over M is equal to MA. Oh, sorry, EE equal to MA. And we substitute in the current density, we substitute in the conductivity, and we get the final formula. Final formula show that these two final, the two final last two steps show that the conductivity of the material and the resistivity of the material in the expression of the electric field. Now, how about resistivity and the temperature? We also learned in Form 5, the temperature will affect the resistivity. As we learned before, the temperature is directly proportional to the resistance. So this means that resistivity also is directly proportional to temperature. Let's see. When the temperature increases, the number of collision per unit times between the free electrons and the ion also increase. The mean free time T will decrease. Since resistivity is equal to M over NE square, okay, over N over E squared over T. So the resistivity from here, we notice that it's inversely proportional to T. So this means that when the T increase, this means the temperature will increase with the time, right? The longer the time as the conductor exposed to the current, this means that the temperature will increase. So when the temperature increase, time increase cause the temperature increase, and temperature will cause the resistivity increase. Okay. So now, sorry, time increase. Okay. When the temperature increase, the number of collision per unit time between the free electrons also increase. Okay. Now, from here, we go to the next slide. Let's observe again. How about the temperature? So electric field, still in the same direction, right to left. And the negative charge always opposite, move in opposite direction to the electric field with a velocity. We call that is the drift velocity. In low temperature, let's say in low temperature, the charge move with certain velocity. How about the temperature? I'm going to increase the temperature. When the temperature increase, we notice that the atom of the conductor, atom of the material, the vibration of the atom increase and cause the electron move slower. Why? This means that when the temperature increase, the resistance also increase, and the resistivity increase and cause the velocity reduce. The graph of the resistivity against the temperature. When the temperature increase, resistivity also increase as well. Means that resistivity is directly proportional to the temperature. As a conclusion, we can say that the conductivity of a material is related to the mean time between the collision by the formula where conductivity equal to number of electron times with the charge for single electron, okay, square. Okay, square of the single charge times with the time mean time collision divided by the mass of the electron. And the resistivity of the material is related to the mean time between the collision by the formula where the resistivity is 1 over conductivity. Okay, and we get that resistivity is the reciprocal of the conductivity, where resistivity means that resistivity is inversely proportional to the conductivity. The resistivity of material increase when the temperature increase because the increase of vibration of the metal ion impedes the drift of the free electron through the metal. This means that when the resistivity increase when the temperature increase. Why? Because the vibration of the ion in the conductor, reduce or effect reduce the drift velocity of free electron, okay, through the metal when it's in the electric field. Let's go to the next slide. Let's say we notice that we will go through the we are going through the semiconductor now. In this world, we have conductor, we have semiconductor, and we have insulator. Conductor, what is the definition of conductor? Conductor with low resistivity or low resistance. Insulator with the very high or high resistance and high resistivity. Semiconductor have the resistance in between the conductor and the insulator. Okay, the semiconductor, actually the resistivity can be changed by doing something. So let's look at the semiconductor. Semiconductor, as we know that in an atom, the valence charge, the charge at the outer shell is 4. If less than 4, there is a metal. Okay, more than 4, that is, okay, for example, 5, 6, 7, that 7 electron at the outer valence, outer shell, that means that it is non-metal. Where any material with 4 electrons at the outer valence, it is considered is the semiconductor. Let's look at the animation. If one of the electron released from the semiconductor, that means that what happened? This free electron can move in the semiconductor. When one of the electron free out, or when the semiconductor not enough one negative charge or electron to reach the octet state, so the free electron will move. Okay, this process we call that is the doping process. Doping process means that the semiconductor is in the condition less 1 electron, okay, less 1 electron to form the p-type semiconductor, or extra 1 electron to form the n-type semiconductor. Okay, the conduction by host. Host means there is a positive charge. Okay, we assume that there's positive charge. So now we look at here. The electric field, let's say the electric field is in such direction. Once the electron move through, okay, just now the electron out, so the electron beside will jump and fill in the